what is important here is that if we have a thin film in a parallel field, we know that we can greatly increase the onset of penetration of vortices, the field of, because in the end, what we want to avoid vortices if we want to probe the Meissner effect. The same way as in cavities, we want to avoid vortices because they're bad. And we do something like this to avoid vortices. And we do the same in nonlinear Meissner effect. We want to delay penetration of vortices, and that's why we take the film, which is smaller than the London penetration depth. This is a dirty film with a penetration depth about 200 nanometers. Our film is about 65 nanometers thick. So if we can see nonlinear Meissner effect, we can, at the same time, we can tell at what field vortices start penetrating in this film. We can do a little bit more than I just showed before. We can calculate the field dependence of the penetration depth exactly, actually using the Usadel equations in the dirty limit. I'm just flashing it here. This is a set of nonlinear equations for superconducting Green's function alpha, from which we can calculate the superconducting gap at current. So if we do all that, we basically reproduce the results I showed before. It's quadratic in field. It has this angular dependence. And we can also calculate these constants C1 and C2. They are of the order of 1. So actually, we don't have any fit parameters here. And here's the experiment. Now, this is a frequency shift as a function of H3. H3 is a small component perpendicular to the field. Why do we need it? Because we don't know where the 0 is. So we have to tune it and see how the shift depends on the perpendicular component. And it's linear, and then it has a cusp. And then it goes down. So once we reach the cusp, we know that we're in the Meissner state. This is a Meissner state, where we're exactly parallel to the film. And we can do it for different DC fields. Now, what's interesting is that the Q factor here stays more or less flat, from 0 to about 1 Tesla. So HC1 in niobium is only, 150 millitesla. So we are well above HC1, which is about 5 times more than HC1. And that is not surprising because it's a thin film, so we know that HC1 should be enhanced. If we use the formula I showed before, BC1 should be about 0.6 Tesla. Actually, we can go almost to 1 Tesla with no sign of penetration of vortices. And then once we exceed 1 Tesla, the Q factor drops, and this cusp disappears. So we know that vortices start penetrating in the film. So that shows that we indeed can delay penetration of vortices, well, to the film, which is almost 5 times HC1 for the bulk film. Now, shown here is the field dependence of this frequency shift. This is B squared. Now, the frequency shift is nicely quadratic, as it should be. This is B squared. And we can do it for different angles. And we have this curve. And this is nothing but this function. So the agreement was surprisingly good, and we don't have any fit parameters here. So basically, we can describe the whole set of data pretty much with no fit parameters, which shows that indeed we're dealing with nonlinear Meissner effect in a dirty film, and it gives us a quadratic pair breaking effect. The pair breaking effect is quadratic in magnetic field. Now, what does it do to RF? Well, it can have some important implications. Let me first remind you basic features of the surface resistance in RF. The surface resistance is due to thermal excitation of normal electrons through the superconducting gap. And we have 2 limits here. We have the clean limit and we have a dirty limit. In the clean limit, there's a conventional to liquid type formula. Rs is proportional to lambda cube and the normal state resistance. If we go to the clean limit, in the clean limit, we are in the normal skin effect regime where the mean free path becomes irrelevant. And what we have a scattering of these quasi-particles on the gradient of the RF field. So as a result, the surface resistance becomes independent of the mean free path, and it's simply constant, which is independent of the mean free path. And here's a formula from the Bardeen and Matisse and Bardeen and many others. It's proportional to lambda to the fourth instead of lambda to the cube here. So in the clean limit, basically the impurities are not important, and non-magnetic impurities also don't affect the superconducting gap. There's an Anderson theorem which tells us that non-magnetic impurities don't suppress the superconducting gap. So the superconducting gap stays the same as we change the impurity concentration. I stole this slide from Enzo, and it shows the surface resistance as a function of the mean free path, and it has this shallow minimum, which comes from the BCS theory. And here we're in a anomalous skin effect, the clean limit, and then it increases for the dirtier sample. Now, if we calculate the surface resistance in the clean limit, what we have here is the spectrum of the quasi-particles, the blue and the red, simply for two different orientations of the field. Here's a spectrum shifted. This is a Doppler shift, and this is a superfluid velocity. Now, if for the field up, we have the blue spectrum, like this and like that. And then when the field changes direction, it swings to the right position. So basically, we have a rocking electron spectrum like this. And then we can see here is that here's what electrons have to activate through. This is the instantaneous gap. And instantaneous gap is suppressed by this Doppler term. So as we increase the superfluid velocity, the instantaneous gap decreases, so more and more electrons can activate, and the surface resistance will increase exponentially. But the superconducting order parameter stays the same. There's no effect of the current on the superconducting order parameter. So this guy is the same as for zero current. But what electrons see when they activate, they see a reduced gap like this. This is a clean limit. In the dirty limit, we have a different situation, because in the dirty limit, non-magnetic impurities become pair breakers, as I showed before, because we have nonlinear Meissner effect. Nonlinear Meissner effect means that the superfluid density is reduced by impurities if we apply current. As a result, we can simply take a formula for the surface resistance and say, now my lambda and delta are functions of H. And from the results I showed before, lambda increases quadratically, and the superconducting gap also decreases quadratically. And that gives us the surface resistance which increases exponentially like this. And that might explain the high field Q slopes and dependence of the Q factor on the field, simply because if there is a dirty layer near the surface, there's pair breaking effect as we increase in field, and that produces this kind of behavior. So the conclusions: dirty niobium surface can result in a nonlinear Meissner effect, in which you can induce pair breaking by applying strong RF drives, and that can give rise to intermodulation effects, generation of higher harmonics by RF current. And that might be responsible, at least partly for possible high field Q slopes. And measuring of the nonlinear Meissner effect revealed 5-fold increase of the vortex penetration field in the thin niobium film. Thank you very much.